Welcome to The Explainer. Today, we're diving into a genuinely fascinating engineering pivot. We are looking at exactly why Caterpillar had to completely rebuild its high-speed, mission-critical power generation platform from the ground up. If you've spent any time working in power gen, marine, or offshore industries, you already know the legacy machines. But today, we're looking at the massive architectural leap it took to hit entirely new thresholds of performance.
To really get why this matters, I want you to picture two gensets sitting on the exact same size skid, inside the exact same size container. One of them cranks out 2,000 electrical kilowatts. The other, it makes over 3,100. That is 50% more power, but with literally zero more floor space. And here's the kicker. That's not just a slightly bigger engine stuffed into a tight box. It's a smarter, entirely re-engineered platform. It is the C175-16.
Section 1. Breaking the power ceiling and pushing past the spatial limits of the 3500 series. So why did Caterpillar have to rethink the whole shebang? Well, think about data centers, offshore platforms, or critical infrastructure. They desperately need more power to keep up with modern demands, but their physical, mechanical footprint, it cannot grow. Real estate on an offshore rig or inside a data center mechanical room is insanely expensive and strictly limited. This created a hard ceiling that the legacy 3500 series just couldn't break. So to solve this, Cat designed the C175 to deliver way more electrical kilowatts per cubic meter of installed footprint than any prior high-speed engine in their lineup. It was built specifically to blow past that spatial ceiling. To put that into perspective, an offshore platform that used to need 3 3500 series gensets to cover its peak load can now do the exact same job with just 2 C175s. That means less deck space, less weight, and fewer machines to maintain.
Moving to Section 2, the math behind the muscle, and how a seemingly minor bore increase radically compounds.
Let's look at the actual geometry here, because the secret to this massive leap in power density is all in the cylinders. The C175 increases the bore from 170 millimeters in the older 3516B up to 175 millimeters. Now, 5 millimeters doesn't sound like a lot, right? I mean, it barely sounds like a rounding error. That is, until you look at the total displacement jump, which leaps from roughly 69 liters all the way to 85 liters. So let's break down exactly why that happens.
This brilliantly illustrates the physics of displacement. Because volume scales with the square of the radius, a mere 5 millimeter bore increase, when combined with a longer 220 millimeter stroke, compounds dramatically. You go from 4.3 liters per cylinder to a swept volume of 5.3 liters per cylinder. Multiply that extra surface area across 16 cylinders, and bam, you jump to a total displacement of roughly 85 liters. More displacement means more air and fuel burned per cycle, which translates directly to more combustion force converted to crankshaft torque. And the best part? You get all that extra muscle without needing to spin the engine faster or add more cylinders.
But you can't just create that much more combustion force and expect a standard engine block to hold it together. To survive the extreme forces generated by burning that much extra air and fuel, the core architecture had to be completely toughened up. We're talking about a high-tensile strength ferrite ductile cast iron block, which offers incredible resistance to stress cracking. This rigid block supports the cylinder liners way better, leading to enhanced head gasket sealing capability. Throw in a forged steel one-piece piston design and quad-turbocharged air-to-air aftercooling, and you've got a beast. Every single structural element had to be engineered to handle the brutal realities of an 85-liter displacement running at absolute peak load.
Section 3. The fuel system evolution, leaving mechanical unit injection behind.
Now, here's the thing. More displacement is only half the equation. You also need a fuel system capable of precisely feeding those massive cylinders while simultaneously meeting strict modern Tier 4 and Stage 5 emission standards. The older, totally forgiving mechanical or hydraulically actuated unit injectors, the MUI and HUI systems of the 3500 series, they just couldn't hit the required injection timing precision. They were reliable, sure, but they completely lacked the microsecond control needed for today's ultra-clean combustion targets. So making the shift to a high-pressure common rail, or HPCR system, it wasn't just a nice upgrade, it was absolutely mandatory.
Consider this staggering figure for a second. 180,000 kilopascals. That is over 26,000 psi. This common rail system is a double-walled delivery setup that provides constant pressure to all injectors at that rating. It is an extreme environment, to put it mildly. It's an incredible feat of engineering that allows for perfect fuel atomization, but, and this is critical, it is also a serious safety hazard. At 26,000 psi, fluid injection directly into the skin is a very real danger.
You are literally dealing with aerospace levels of hydraulic pressure here.
Which brings us perfectly to our final section, Section 4, a new maintenance mindset, dealing with the operational reality of tighter tolerances.
I really want you to ask yourself this question. Can you service a C175 the exact same way you service a 3500? Honestly, the single most dangerous thing a veteran power generation technician can do is assume their service habits from the forgiving 3500 series will carry over to the C175. When you push a machine to these absolute engineering limits, the way you maintain and interact with it must fundamentally evolve.
Let's look at how this translates into strict new operational realities on the shop floor. First up, extreme sensitivity to debris. That 180,000 kilopascals common rail fuel system we just talked about, it will fail catastrophically if exposed to even the absolute smallest amount of contamination. Absolute cleanliness standards are now required. Second, you are dealing with significantly heavier components. The cylinder heads alone are about 50% heavier than the 3500 series, which means you absolutely need dedicated lifting devices. And third, higher temperature fuel handling. High pressure means high heat, and this system handles fuel up to 55 degrees Celsius or 131 degrees Fahrenheit, so everything is heavier, everything is hotter, and everything is under way more pressure.
To put it all into perspective, think of the 3500 like a super reliable pickup truck engine. It is proven, it's forgiving, and it's built with a really wide margin of error. The C175, on the other hand, is much more like a Formula One power unit that's been adapted for endurance racing. It extracts maximum output by optimizing every single component to the absolute edge of its tolerance. Yes, that means you get 3,100 kilowatts in a 2,000 kilowatt footprint, but it also means there is exactly zero room for sloppy maintenance or shortcuts. Like, you can't just bypass a filter for a quick test run. You will completely destroy the high-pressure pump. So as we wrap up this explainer, I want to leave you with this provocative thought. Are your service habits genuinely ready for zero-tolerance engineering? Because the leap from the 3500 to the C175 wasn't just a step up in power, it was a total paradigm shift in mechanical design and operational discipline. You really have to consider how your approach to precision, cleanliness, and safety must change to master this incredible architectural leap. Because honestly, hitting these extreme pressures and this level of power density is only possible through metallurgy and cooling techniques we've quite literally never seen before. But hey, that is a topic for our next explainer. Thanks for joining me, and keep that standard of excellence high.